Okay, so hello everyone. I'm pleased to have this occasion to talk to you about this work on constraining complete argumentation frameworks. So as you can guess, it's built on the famous Dung's framework for abstract argumentation. So I will give a few basic notions on this topic before actually describing my work. So I guess it's now a well-known framework. So we use directed graphs where nodes represent abstract arguments and the edges between nodes represent the attacks. And the notion of acceptability of arguments, which is usually used, is based on collective acceptability of arguments, which means that we want to identify sets of arguments that are jointly acceptable. For instance, here A3 and A4 are acceptable because they are not attacked. So A2 is rejected because it's attacked by two accepted arguments. And then A1 is accepted because its only attacker is rejected. So this property of joint acceptability is usually characterized by some basic notions like conflict freeness, which means that you don't want to accept together some arguments which attack each other, and admissibility, which means that besides conflict freeness, you also want to accept sets of arguments if they are able to defend themselves against attackers. Then from these basic notions, we can define some classical semantics by adding some other constraints like maximality and so on. So here the point is not to give a full description of argumentation semantics. Let me just mention that for classical reasonings, the complexity may be quite high even for these basic semantics, because for instance, credulous acceptance, which means determining whether an argument belongs to some extension of an argumentation framework, is NP-complete for most semantics. Only the grounded semantics is polynomial. And we also have co-NP completeness or even pi2p completeness for some semantics when we consider skeptical acceptance, which means determining whether an argument belongs to each extension. Then the model proposed by Dung has been extended in various ways. In this talk, I'm interested in incomplete argumentation frameworks. There are a generalization of Dung's model where we add two kinds of uncertain information. We have, so the dotted arrows, I will use them for representing uncertain attacks, which means that we are not certain whether this attack from A3 to A2 actually exists. And then this square dashed argument means that we are not certain whether the argument A4 actually exists. Let us notice that if it exists, then it certainly attacks A2 because this arrow is a normal plane arrow. For reasoning with this kind of model, usually we use a notion of completion, which are argumentation frameworks that can be somehow derived from all the uncertain information which is encoded in the AIF. So for instance, here we have the completion where none of the uncertain element is added, which means that we don't have this attack from A3 to A2, and also we don't have A4. And obviously, if we don't have A4, we don't have either the attack from A4 to A2. So here we have in total 4 completions. This one can be seen as the minimal one, and this one, the maximal one, where all uncertain elements actually appear in the graph. For reasoning with this kind of set of completions, similarly to credulous and skeptical acceptance that can be used when we have several extensions, here we have what is called the possible view and the necessary view. The possible view means that we are interested in some properties that should be satisfied in at least one completion, and the necessary view means that the property of interest must be satisfied in each completion. And the property of interest can be more or less any property of argumentation frameworks. For instance, the credulous or the skeptical acceptance of a given argument. So here, if we look at argument A3, we see that it's accepted, it's skeptically accepted in each completion because in all of them, it's unattacked. So we'll say that it's necessarily skeptically accepted. Then A4 is skeptically accepted only in some completion, because obviously it's not accepted in the completions where it doesn't appear at all. A2 is credulously accepted in some completion, only this one, but for instance, not the second one. And then A1 is credulously accepted in each completion. So we have the 4 levels of acceptability that have been defined for arguments in incomplete AFs. So in the rest of this talk, I will focus on 2 of these forms of acceptability, namely the possible credulous acceptance. So looking at an argument being in some extension of some completion, and on the opposite side of the spectrum, the necessary skeptical acceptance, which means that we will look at arguments being in each extension of each completion. So the complexity of these problems has been determined. In most cases, it's the same as for credulous and skeptical acceptance in classical AFs. We just see that now the grounded semantics is also at the first level of the polynomial hierarchy. So I'll finish the background part of this talk by describing some of my previous work, which served as motivation for this new work. It's a problem that we encountered when working on the revision or the merging of argumentation frameworks. In previous papers, we proposed adaptations of AGM revision or of belief merging, where we have as input an argumentation framework and a propositional formula. From this, we have a first step based on the classical AGM revision, where we obtain a set of revised extensions, which somehow corresponds to the set of revised models that you have in actually in Katsuno and Mendelssohn's revision, not AGM. And then the second step consists in generating a set of argumentation frameworks such that their extensions exactly correspond to the ones that we obtained at the first step. And we can do similar thing with belief merging. The problem is that here we need a set of argumentation frameworks and not a simple graph, because not all set of extensions can be represented by a single argumentation framework. For instance, suppose that the result of the revisions part, so the first step is this set of extension. It's known that it's not representable with a single argumentation framework. So for instance, under the preferred semantics, but also for other semantics, because A1, A2 is included in A1, A2, A3. So it's something known in the literature. But if we use 2 argumentation frameworks instead of a single one, it's doable. For instance, this first AF has one preferred extension, which is A1, A2, and this second AF has one preferred extension, which is A1, A2, A3. Which means that we can also represent it with one single incomplete AF, because this incomplete AF has precisely 2 completions, which are these 2 argumentation frameworks. So the question that came to my mind when working on this problem was, could we use one incomplete argumentation framework to represent any set of argumentation frameworks, or also any set of extensions? So on a simple example, we can see that it's not the case, actually. The incomplete AF model does not work for this purpose, because let's consider, for instance, these argumentation frameworks. A1 here is attacked by A2. In the second case, it's attacked by A3. If we want to have one complete argumentation framework for that, we should have A1 as a certain argument, because it's in all the completions of the expected incomplete AF. And then we see that since A2 is not in all the completions, it should be uncertain. Similarly for A3, but the attacks are certain. But now with this incomplete AF, there's a problem. We have 2 additional completions which are not in the initial set of argumentation frameworks that we want to represent. So this is why I tried to solve this problem and to introduce constrained incomplete argumentation frameworks, which are a generalization of incomplete AFs, where we had a propositional formula which will be used to select a subset of the completions, which are those that we actually want to represent. So this formula is built on a propositional language where we have 2 kinds of variables. The first one, the arg A, for each argument A in the incomplete AF, means that the argument A must appear in the completion, and similarly, ATT of AB means that the attack from A to B must appear in the completion. The other components of the constrained EAF are the classical parts of an incomplete AF, so classical arguments, uncertain arguments, classical attacks, and uncertain attacks. So if we come back to the previous example, we have this incomplete argumentation framework. We can enrich it with a constraint, which is an exclusive OR between arg of A2 and arg of A3. And now among the 4 completions that we had on the previous slide, we only have 2 of them, which are the ones that we wanted to represent. So the question now is, can we do the same thing for any set of argumentation frameworks? And the answer is yes. So here is a method that allows to do that. The idea is to define a propositional formula in the language that I defined that will represent precisely one argumentation framework. In the later step, it will be used to represent one completion of the incomplete AF. So given an argumentation framework, we simply want to have all the arguments that appear in it that must be positive in the propositional formula. The arguments that do not appear in the argumentation framework must be negated here. And we can do the same thing with the attacks. So it's easy to see that this formula will only be satisfied by one argumentation framework. So for instance, here we can say that we want to have A1 and A2, but we don't want to have A3. And we want to have the attack from A2 to A1, and we don't want to have all the other attacks. So we can do the same thing with the other completion of the incomplete AF in the previous example. And now if we want to represent both these argumentation frameworks as the completion of a single constrained AIF, we can do it in several ways. A very naive one consists in having all the arguments and all the possible attacks defined as uncertain. But then we had a constraint here which will allow to restrict the set of completions to only the AF which satisfies this formula and the AF which satisfies this second formula. So exactly the completions that we want. A slightly less naive solution consists in fixing the certain elements as we did previously, but then again, the same constraint can be used to select the completions. So the strong point of this part is that actually any set of argumentation frameworks can be mapped to a constraint AIF such that its completions correspond to the initial set of argumentation frameworks. So then the goal is to do the same thing for representing any set of extensions. So here it's quite simple because for any set of extensions, we can map it to a set of argumentation frameworks such that each of them correspond to exactly one of the extensions. So on an example, it might be a bit easier to see. Suppose that we have A1, A2 on the one hand and A2, A3 on the other hand. We can define here this argumentation framework built on the whole set of arguments where all the arguments of the extensions attack the arguments which should not be in the extension. So here, this AF exactly corresponds to A1, A2. And on the opposite, here, this argumentation framework corresponds to A2, A3. And this can be done, of course, for any set of arguments, which means that this set of argumentation frameworks now can be mapped to a constrained AIF if we use the previous result. So this is the second strong result that I wanted to show when working on this issue of how to represent in a compact way the result of the revision or the result of the merging of argumentation frameworks. So there are, of course, some open questions related to this issue, especially looking at the compactness of the result. Here, the goal was only to prove the existence of a constrained AF for representing any set of AFs or any set of extensions, but it would be better, of course, to have a more compact representation, or at least a better representation following some criteria. For instance, for having the best graphical representation, an idea could be to use some notion of distance minimization, which is usually used in belief revision or belief merging, like it was in this paper on merging of argumentation systems. And regarding the propositional formula, so the constraints in the constraint EAF, of course, here the first approach provides a quite naive representation of this constraint, but some topics like knowledge compilation could be used to provide a better formula with respect to properties like its size or the computational complexity of reasoning with this formula. So I studied the complexity of possible credulous acceptability and necessary skeptical acceptability, and I proved that it actually stays the same as in the case of classical incomplete AFs. Intuitively, it's because checking whether a completion satisfies the constraint is polynomial, exactly as in classical propositional logic, it's polynomial to check whether an interpretation satisfies the formula. So adding this propositional task does not actually increase the global complexity of reasoning. So to conclude, this model is very useful for increasing the expressivity of incomplete AFs without increasing the complexity. Something which is not in the talk because of time constraint is the possibility to encode some new kind of extension enforcement with these new constraint AFs. And so as future work, I would like to design some methods for choosing the optimal constraint AF. As I said, maybe using some distance minimization and some methods from knowledge compilation. And of course, implementing revision or merging operators or extension enforcement operators based on this new model seems to be quite appealing. So thank you for your attention, and I'm done.
Thank you, Jean-Guy. I see 2 questions online. Is there a question in the audience? I don't think so. So Dov Gabay was the first. Please go ahead. Please unmute yourself.
Yeah, okay. I have 2 comments, stroke question. One, am I correct in understanding that your choice of the extensions that you want and don't want is done in the meta level? You write formula of classical logic or something, and then you use it to combine the networks and then choose. Is that correct? You don't do this by having a single network with additional points that will have the extensions you want.
So it's not for selecting extensions, it's for selecting completions. So for selecting some of the graphs, if you look.
Yes, you do that in the meta level.
Yes. This formula is aside from the.
Okay. So in the meta level, it's always easier to do, but it is a good idea. The question is, some applications wouldn't want things done in the object level. I mean, suppose you're a politician and you see an extension from the arguments you put forward that attack each other. You can't do this in the meta level. You want to add more arguments that will cancel that extension. So this type of another thing why the meta level is too powerful to do things is, I mean, you have probabilistic argumentation, you have numerical fuzzy, I mean, whatever, all kind of extras. All these extras are done in the object level. So you lose that idea, how you'll have to bring all of these into the meta level. It's a huge task. And so.
Because of the time.
Okay, I stop now. Thank you.
Thanks.
Oh, you don't have anything to say, Jean-Guy? I think there was one further question. So one hand online, but it may have been put down already.
Well, I can't see any other one.
No, if not, then let's thank Jean-Guy again.
Thank you.
Oh, sorry, Nico has a question.
Okay, sorry, yeah, Nico, sorry.
Oh,
Please make it brief.
Oh, I was just clapping.
I had a question, but okay, maybe a quick one. So I was just wondering about the complexity. So you mentioned things like computing the minimal formula that restricts the possible instantiations, and then perhaps finding a most compact CIAF. So do you have any ideas based on related work what the complexity could be?
Not yet. I haven't had time at all to think about it.
All right.
Thanks.
Then we can go to the second speaker. That's Leela Amgul. Leela, are you there?
Yes.
Oh, yeah, I see you. And the title of your talk is Non-Monotonic Explanation Functions. Please go ahead.
Okay, thanks. Doesn't work. Do you see the full screen?
Control L.
It doesn't work.
Maybe you should click the window and then
Afficher.
Start from the button, right?
I can see the slide.
Mode de plein écran.
À gauche, plein écran. On the left. On the left.
Control L on the left pane. Control L. Mode plan écran.
Yeah, but it does. Now it works. Perfect. Thank you. Sorry. Hello, everybody. So I will speak about, my talk is about explainability in AI. So we know that there are very great advances in data-driven AI, in machine learning, in different domains, especially image recognition, etc. And there are a lot of models that have been proposed. Some of them are, we say, interpretable in the sense that their inner reasoning can be understood. Example, like for instance, decision trees, Bayesian networks, etc. While others, like deep neural networks, are non-interpretable. We say that even the designers are not able to understand how the model works, why it produces some results, etc. So whatever the type of these models, so explainability is needed. So we need to know why a model produces a result. And this is important for improving trust in decisions made by those models and also for giving feedback for users. So for instance, so explainability, it answers the question why a model produces or predicts some result. For instance, if we have a model, a classifier, which for instance, in this case, we have, for instance, we have a person which is not in vacation, which there is no concert and the person has a meeting and there is no exhibition. So the model predicts that the person shouldn't go for hiking. So we would like to know why the model gave such prediction. In this case, I have a neural network which predicts a bird for this image, and we would like also to know why this image, the model produces bird instead of cat or dog or whatever. So there are two approaches for explainability. For explaining a model, we have two approaches. The first one is trace-based, what we call trace-based approach, which consists of explaining the inner reasoning of the model. So what we do is exactly to describe the algorithm behind the model, okay? So what the advantage of such approach is that it produces the real explanations because we would like to understand why a model produces an output. And this is when we describe the reasoning of the model, if we do it properly, we produce the exact answer. However, this approach is only feasible for what we call interpretable models and not for the other ones. And the other ones, generally in this machine learning literature, they are the ones that are very efficient in different applications. So to solve this problem, there is another approach which consists of taking only the input from the input and the output that are produced by the model We completely abstract from the inner working of the model. We only consider input and we see what is the output predicted by the model, and we try to define explanations from it. And the well-known approach is to produce what we call minimal sufficient subsets in the literature, which are the key features from the input that lead to the output. The advantage of this approach is that it's feasible even for non-interpretable models, as I said. However, it may return some incorrect explanations. For example, this is the case of the well-known Anchor model, and it may return correct, but non-feasible in other non-feasible solutions. So the contribution in my presentation, what I did is to investigate these abductive explanations, which is only one particular type of explanations. I investigate these abductive explanations for complex classifiers, which means for black box classifiers. I don't have any information about their inner behavior or inner reasoning process. Okay, so what I do is to introduce two properties, which are the first one is coherence. I will come back to it. So it's a very important property that a model should solve. The second one will just characterize this kind of explanation functions that we need. It is non-monotonicity. I will come back later to see why functions are non-monotonic in this case. Then I define the notion of absolute explanations, which are in some sense the real abductive explanations, and that are not feasible. But this is what I said before. We see that these are the real explanations, but unfortunately not feasible, and we will see later why. Then the second thing is to introduce plausible explanations, which are those that characterize in some sense explanation functions for complex classifiers. And we show that the existing models, Lime and Encore namely, are monotonic and violate coherence. This is why they produce incorrect explanations in some cases. And then I introduce what we need. What we need is to define non-monotonic functions which satisfy coherence. And this should approximate these absolute explanations because these are the ideal ones, but unfortunately we cannot compute them in practice because, as we will see, they need the whole feature space, etc. So to describe what is a classification model, so we have a set of features. We have a domain for every feature. For instance, it can be a binary or whatever. So what we call literal is any pair at feature and the value. For instance, vacation can take value 1. This is one feature. Vacation can take value 0. This is another feature, etc. A feature space, what is it? It's all the possible assignments of the different features. Okay, and we have a set of classes, which we may have binary classes if we have only 2 classes, like in the example. And the classifier is simply a function which assigns to every instance a class. Okay, so another important property for me is this notion of consistency. We say that a set of literals is consistent if it doesn't contain 2 literals for which assign for the same feature 2 different values. Very simple concept. Okay, so what is now an explanation function? An explanation function is a function which assigns to every instance a set of sets of literals. Okay, so and also particularity of an explanation function is that explanations are generated from a subset Y, from a subset of instances. So what is the first property? The first property of coherence, it says that if I generate, for instance, if I have H is an explanation of an instance X, I have H prime, which is an explanation of another instance X prime. Then if the union of the 2 is consistent, then the 2 instances should be assigned the same class. to show the example here, for instance, if for instance we say that the fact that the person has no vacation is an explanation for assigning 0 to instance 1, and if the fact that the person hasn't a meeting is an explanation for the instance x2 for getting the class 1, as you can see that the union of the two is consistent, then why this case is not interesting? Because since it is consistent, then we can find for sure another instance x, which contains this element. And in this case, V0 cannot be an explanation for 0 and for 1 at the same time. So we get this inconsistency. So this is basically what this property of coherence says. The second property of monotony, what it says that the generation of explanation is monotonic. Okay, so if for instance I generate an explanation from a set Y, then if I extend the set Y by other elements, so I get another set Z, so the same explanations should remain also, should be generated from Z. It is non-monotonic otherwise. We will see that explanation functions are non-monotonic in nature. We'll see why. So let's start with what is an ideal abductive explanation. So if I consider a subset, assume that I have a subset of the feature space, then an absolute explanation is a minimal set of literals such that always lead to the same class as X. Okay, so whatever the instance in which contains the subset H, then this instance has the same. What we can remark here is that this definition checks the whole space, feature space. This is what I put here in orange. As you can see, whatever Y belongs to X. So to get this absolute, I need to check all the feature space, which is not feasible, which is impossible in practice. This function is coherent as monotonic because it checks for the whole set. So here, on my previous example, I cannot check because I don't have the whole feature space. I don't have the elements of the model. But for instance, for this very simple example, as you can see here, for the class C3, for the instance, for instance, X4, what we can see that the fact that feature 1 gets value 1 is the explanation, is the only explanation of this instance. So since these absolute explanations are not feasible, so we just focus on this set Y. We check only the instances in the set Y, okay? So we get these plausible explanations. They are plausible because we will see later that they may not be always correct. So the function is incoherent. Such function is incoherent, okay? We can for sure find a classifier. We can find a theory in which it doesn't work. It is non-monotonic as well. So let's see why it is not coherent. For instance, in this example, so you can see for X1, it has this U1 as explanation, which is V0, and you have X2, it has U5, which is N equal to 0. The union is consistent while the two instances have opposite classes. So there is error. U1 and U5 cannot be explanations in this case. And why it's not monotonic? Because by definition, here you can see that X5 has U3 also as an explanation. But if I add the X8, I add a new instance, which is X8 here, you can see that U3 doesn't belong, is not an explanation because it doesn't verify the condition here. There is some condition. What is C1, 1 and 0, 1 and exhibition 0. You can see here that here it's I have 1, 0, but it's not the class is different. Okay, so so this explanation functions. Such explanation functions are not monotonic. So now what we can summarize here is that having absolute explanations satisfy the property, but it's not important, it's not interesting because we cannot check all the whole feature space, which is impossible. Plausible explanations are non-monotonic, and this is for sure what we should get because we cannot check the whole feature space, but this what we have actually as they violate coherence. So we propose a solution which is non-monotonic and in the same time satisfies this coherence property. I propose here a very naive solution that, which consists of built-in arguments. An argument here are the plausible explanations for classes. Okay, so we have an argument which supports a class. Okay, so we have the different, we have here 8 arguments. And then I define the notion of attack. 2 arguments attack each other if the coherence property is violated, which means that the union of their supports is consistent while the classes are different, and they get this one. And since this attack relation is naive, is symmetric, so as you know, so in Dung semantics, so when this attack relation is symmetric, so it's stable preferred coincide with this naive, which consists simply in defining maximal non-conflict free sets of arguments. And in this case, I get 4 maximal conflict free sets of arguments. Okay, and then what is now the explanation function? An explanation function, it's a function which returns the supports of arguments in favor of the class of X, which belongs to all the extensions. This is a cautious definition because we are used in non-monotonic reasoning to have this cautious approach for reasoning with conflicting information. This is helpful in the sense that the function I got is coherent and not monotonic. But this cautious reasoning has some drawbacks, which is the fact that in my example the intersection is empty. So so it may return empty explanations. So no explanation for. In this case, for all the examples, actually. So this is the drawback of this cautious reasoning. So in handling inconsistency, it's a suitable approach, while in classification, especially when we look for explanations, we should provide explanations. So so this is the purpose of providing explanations, and to return an empty set is not good. So we can refine the approach in different ways. For instance, I just give here an example. As you can see here, we have 4 extensions. The first one supports only the class 0. The second one supports the 2 classes. So there are arguments in favor of 0, other in favor of 1. The last one, only the class 1. For instance, we can select one extension among those that maximize the number of classes. For instance, we can choose this the set E2, and we work only with this extension. So there are different, we can improve. This is just a very preliminary work, as I said, but it shows, in fact, different things. The first one is that generating abductive explanations for black box classifiers consisting of reasoning under incomplete information. So we have non-monotonic functions for which we should ensure consistency. And here we can use the different techniques of NMR for defining such explanation functions. So for perspective, there are a lot of perspectives because, as you can see, it's still preliminary. There are a lot of things to be done. So we need to define novel explanation functions that guarantee, of course, the existence of explanations, which is very important, and in the same time to approximate absolute explanations, because since they are non-monotonic, we have seen in my example that we can provide for a subset, if we consider a subset of instances, we can provide one explanation. And if we get novel information, for instance, about the model, then that explanation should be rejected. So we can provide at some time, we can guess that at some moment, we can provide the user a wrong explanation just because we don't have full information about the root behavior of the model. So another very important point is investigating other properties of explanation functions. I am working, actually, I have made some progress on this point because we need some axioms to follow, principles or axioms, or whatever, what is the name we can use, is to have this for guidance, because there are a lot of works on explainability and there are very few properties. What they use in this community of machine learning is metrics for measuring, and I would like to relate them to some more general principles for high-level properties for understanding what is an explanation, what are the properties, and also to facilitate the comparison of the different models that exist. Thank you very much for the attention.
Let the program share. Is there time for one quick question? It was more than 20 minutes.
Maybe just a quick question.
Okay, one quick question. I don't know who was first. I randomly choose Nikki Pfeiffer. Sorry.
I was just clapping. No question. Thanks.
News? Question? Or everybody was just clapping? Okay, no question here. Maybe a very quick question. Oh, yeah, sure, John.
Okay, so thank you, Leila. So you have some properties that your classifier needs to satisfy in order to show the results. So did you have a look at the most famous, the most used classifiers to see if they're satisfy those properties?
I don't define properties for classifiers, because the whole thing here is that to completely abstract from the classifier. Okay, this is the idea of black box classifiers. We cannot understand their inner behavior, so we completely abstract from them. What I am looking for are the properties of what is an explanation. What is an explanation? What should an explanation function satisfy?
But in some proposition you prove at the end, so hence it's not coherent. So to prove this, you had some hypothesis. If you can prove that it's not coherent.
It's not coherent, it's sufficient to find one classifier. There exist a lot of classifiers that have been trained on different data sets. You can find one classifier in which which has been trained on something. You apply your definition of on that data set, and you will see that you get errors.
Yeah, so there is no constraint. You can have any table.
Yes, yes.
I understand. That answers the question. Okay.
Okay, thank you again, Leila.
You're welcome. Thank you.
The final talk in the session is about a paper by Timotheus Kampik and Dov Gabay. I'm not sure who will present it.
Thank you. I will present it, and Dov is also present for questions and comments.
Okay, so the title of the talk is The Degrees of Monotony Dilemma in Abstract Argumentation. Please go ahead.
Exactly. I'm still waiting for Leila to de-share her screen. Thank you very much.
Okay, sorry.
So, 1 second. Can you see my screen?
Yes, we can see it.
Okay, thank you. Exactly. Thank you for the introduction. I've posted the link to the slides and also to the preprint in the chat, and now we will give a brief intuition of the work that is in our paper. And the general idea is that considering formal argumentation or abstract argumentation as a non-monotonic reasoning approach, we look at dynamic argumentation, where we infer extensions from an argumentation framework using an argumentation semantics. Then we add new arguments to the argumentation framework, and then again infer extensions and so on. And if we have to violate monotony, we want to be as monotonic as possible given the constraints of the semantic. So we in some way want to maximize monotony given constraints. And let me motivate the idea using two simple examples. And here we essentially just look at choice under constraints in this example. So if assume we are a politician P, and at time t0, we promise something, just some abstract set of elements A, B to some lobbyist, so to some agent. At time t, our team proposes to promise something else to our allies, and this something else is either a set of elements A, B, C, D, E, or a set of elements C, D, E, F. And then obviously what we want to do is we want to keep our promises to the lobbyists. And so what we will promise to the allies will be, in this case, A, B, C, D, E. So now let's continue with this. So at time t2, our team proposes to promise either A, B, G or C, D, E, F to the public. And now we are in a dilemma, because we can either maximize the degree to which we keep the promise to the lobbyists, or we can maximize the degree to which we keep the promise to the allies, but we can't please both. And this dilemma also occurs in abstract argumentation. If we, when we normally expand an argumentation framework, I will get to this. And of course, there's no solution to this dilemma, but it's interesting to analyze it. And we also point at upcoming work that we will present actually next month at a different conference, where we have a somewhat practical application for this general idea. Of course, a more realistic application would be, for example, application to knowledge-based systems, where we have an inference engine I that draws inferences from a changing knowledge base that contains some conflicts, so it can be modeled as an argumentation framework. And we have different configuration managers, so other systems that update their configuration based on what the inference engine infers. And then, of course, we know that updating configurations in very complex systems like ERP systems or similar can be very costly, and we just want to be, we want to change as little as possible. So that would be another intuition. I don't need to go through this example because it's the same abstract example as the previous one. So, as I said, we look at abstract argumentation, so we don't consider the structure of the arguments. So we just have an argumentation framework as directed graphs where the nodes are arguments and the directed edges are attacks. And we look at the behavior of different argumentation semantics, and I don't think I need to introduce the semantics. Of course, it's also hard to cover the whole semantics zoo, but we now mostly use the classical Dung-style argumentation semantics. Now, to have some reasonable constraints on how we update our argumentation framework, we look at normal expansions. And generally, an expansion is defined as simply an addition of arguments and a text to an argumentation framework without removing any arguments or text. And the normal expansion has an additional constraint that you are not allowed to add a text between existing arguments. And we think that is this is a reasonable constraint. First of all, we want to be a bit conservative to show that even under some constraints, this dilemma occurs. But also we think that modeling change to an argumentation framework using normal expansion is actually reasonable, because we explicitly model any change that occurs by adding an argument. So we're a bit more transparent about how we change it. And if we want to remove an argument, we can also model this by adding a so-called annihilator argument and so on. So just to give an example, here we have the argumentation frameworks, and we can see that AF or AF prime expands and also normally expands AF. But AF prime prime is only an expansion and not a normal expansion of AF prime, because we add an attack between A and C, although A and C exists already in AF prime. So what we do to change our inference as little as possible, we define cardinality maximal monotonic extensions. So given an argumentation framework and a normal expansion of this argumentation framework, and given a semantic sigma, and given extensions we can infer from both of the argumentation frameworks, we define a degree of monotony for which is for non-empty extensions, the initial extension intersecting with the new extension. And then the cardinality of this divided by the cardinality of the original extension. And so we get the number between 0 and 1, quite obviously. And then we want to select only an extension that maximizes the degree of monotony to change our inferences as little as possible. Now, some people might ask why we use the cardinality maximal approach, which is perhaps less elegant than a set inclusion maximal approach. And we get to this later. So there are some tricks that one needs to apply to usefully define a set inclusion maximal approach. So, and if we apply this approach, and if we start with an argumentation framework that only contains the argument A, and then we expand to ABC, then obviously we are maximally monotonic in the extension we infer, because we only can infer one extension using any reasonable semantics, but also the degree of monotony of A here and ABC here would then be 1. But now if we expand to this argumentation framework, we can, for example, maximize monotony with regard to the previous inference, and this would then also maximize monotony with regard to the first inference, coincidentally. And so, no, actually it would not. So now we are already in the dilemma. So here we can then infer CBD, which would be maximum monotonic with regards to ABC, but would not be maximally monotonic with regard to A. So here we are already in the dilemma. And if we go back to our example, we have the same problem. So we now, in the original example, of course, I was only mentioning sets, but if we would model this as the argumentation framework sequence that we see here, so starting with the framework to the left, then expanding to the framework in the middle, and then going to the framework on the right, we again can either maximize monotony with regards to the extension we would infer from the framework in the middle, or from the framework on the left. So from framework on the left, we assume that we infer AC. And then when we expand, of course, we want to infer A, C, D, E, F. And then when we expand again, if we look at, because we look at cardinality, we would want to infer B, D, E, F using any of the common argumentation semantics. But then we would be more, we would be maximal monotonic with regards to the framework on the left if we would infer A, C, G instead. So here we need to make some trade-offs. And again, to motivate this, of course we want to be maximally monotonic because it makes more sense in regards to some costs that we might have, like monetary cost, time. So there's a monetary cost of change, the time of change, or the time needed for change, the social cost of change. And of course, there's no real solution to this, but we can have optimization approaches or mitigation approaches. And one approach would be to simply have a time to compute the average degree of monotony and then discount it with some time-dependent discount factor. And if we would do this with a discount factor of 0.9, then we would actually here select the extension AGC, that is maximally monotonic with regards to AC, and not maximally monotonic with regards to AC, DEF, simply because if we would select BDEF, then the degree of monotony with regards to AC would be 0. So this would be a harsher punishment. Some theoretical results that we have, so I just give an intuition here, is that all Dung semantics, so all semantics of the initial Dung paper are affected by degrees of monotony dilemma. And quite obviously, the degree of monotony can change can be affected quite drastically, even if you just make relatively small changes, roughly speaking, to an argumentation framework. So by just adding an argument and an attack, which is of course quite intuitive. If we use any of preferred grounded or complete semantics, and we normally expand an AF, and we don't attack a specific extension we have inferred, then we can select a new extension with a degree of monotony of 1 with regard to the previous extension. And this is a property that simply many but not all admissible set-based semantics have, because an admissible set defends itself against all attackers. It intuitively makes sense, but it's not implied by the property of an admissible set. And this observation also reflects the cautious monotony principle, so that monotony is only violated under some conditions that we have defined in earlier work. And this is not the case for many naive set-based and weak admissible set-based semantics, but as I mentioned, also not necessarily the case for admissible set-based semantics, for example, stable semantics. And now finally coming to the question why we don't use subset maximum monotonic extensions. And there the problem is that if we have inferred the empty set, everything that comes is subset maximally monotonic. So in ongoing work, or in work that we will present next month at the Conference of Logic and Argumentation, we address this issue by defining Pareto optimal subset maximum monotonic extensions that can filter out these edge cases. But we assume that even then the degrees of monotony dilemma occur. So there's a relatively simple example that shows this. But with this tweak of Pareto optimality and set inclusion maximality, we actually get a nice application case where we can apply this idea to model burdens of persuasion in abstract argumentation, so for a legal reasoning use case. And yeah, for future work, one could extend this model, so one could consider weights on arguments that indicate the cost of monotony violation, or one could also consider preference on arguments, and this would then really nicely relate to this set inclusion maximality idea. Thank you very much, and please ask any questions if you have.
Any questions online or here? No questions in the room. Questions online? And I have a question about your motivation. You said on one slide you gave various kinds of costs for violating monotony.
Mm-hmm.
And among that was social costs. Could you give a realistic example of social cost of violating monotony?
I mean, essentially the toy example we had was a politician, right? That if we are not monotonous, or if we are not as monotonous as possible, then we are breaking our promises. And of course, this would not really relate to a realistic application of formal argumentation, I would say, because it's hard to, solve these kinds of problems. But if you have an organization and, for example, you do the reconfiguration of your IT systems based on some inference algorithm, then there are also social costs of change, right? Because if the inference implies that people have to change their work routines and so on, this means that you need to change the behavior of the people, and you need to make of your employees or whoever, and you need to make them accept these changes. And this is, I would say, this is kind of a social cost. So it's really hard to estimate in monetary terms, and it's probably easier to regard it as a social cost than as a monetary cost or time cost, to also be more considerate and more empathic to these people.
There are also other examples, if I may add, and this is with court cases and witnesses. If you have a divorce case or any kind of case and witnesses come, and then later on more witnesses come. I mean, you have this with all these scandals about women complaining about a politician that he mistreated them, and more of them come. And they contradict one another, or they don't. You get an argumentation network. And if you want to do it right, you do it in ASPIC. But then the question is, what do you do with these more and more contradicting witnesses? Do you say, case is closed, we have had our verdict? Do you reopen the case? All of these are social considerations. But continuing monotonicity, when you accepted a verdict and you accepted witnesses and so on, don't start overturning it too lightly.
I guess Boris Johnson would not be too happy about that if he is accused by many women. So isn't there an arbitrary element that the thing you start with persists unless you really have to change it?
Yes.
Yes. So of course, this is in a way both a philosophical and a practical concern that one needs to address, but it also depends on how you apply it. So sometimes, of course, we cannot always zigzag around, right? We need to be pragmatic. Once we've committed to something, we need to maintain some kind of consistency. But even for example, in the legal reasoning use case that we have with Giovanni Sato, we actually start with an argumentation framework and we deconstruct it. So we essentially use this idea of maximal monotony as a tool to add a fake dynamic perspective on it. So it's not that we are actually looking at the dynamic scenario, but we can use these dynamic properties as a tool to model, in this case, the burden of persuasion, and to build like a very nuanced perspective on preferences in this case.
Yeah, you see, instead of using, I mean, you can use a predicate. For example, a predicate is a policy of how to look at the value of various elements in the network. And then when you have more elements coming in, if you apply the policy again, it will be consistent, but not necessarily give you a subset predicate consistent. It would be a different predicate that you all the time apply. Like, I don't know, something, if you don't attack anybody, then let nobody attack you and give that preference. So you follow a predicate, and this actually connects with the previous meta level, of Jean, the first lecture of this session, where he had predicates of wanting extension, not wanting extension. So, I mean, one can use some of his results to connect to them.
So there might be a relation with a previous talk. Anyway, I'm afraid we have to stop here. Thank you very much again.
Thank you.